In this chapter, we're going to switch away from equilibrium chemistry and we're going to start to talk about thermodynamics. We've talked about thermochemistry previously when we talked about enthalpy, delta H. But now we're going to introduce two new concepts, specifically entropy, delta S, change in enthalpy is delta S, and Gibbs free energy, delta G, because they give us a more robust understanding of what's going on in the energetics or thermodynamics of chemical reactions. Before we do that, we need to have a general idea of how to frame this discussion and what we're talking about. So the first thing I'd like to present is a slide about energy tax. So if we look here, if we want to turn coal into electricity, we need to burn the coal. All right. We then need to use that heat to heat up water and to turn a turbine. That turbine will then produce electricity, which will go through a transformer. The electricity will then be transmitted to the building where it will be used. And for each and every one of these processes where we convert one form of energy to another, we are paying an energy tax. Said another way, not all of the energy is free. Only some of the energy is freely available to do work, to power something at this building. So we need to consider why some of the energy is not free. We also need to consider that in this case, when we convert from energy from one form to another, we lose heat, right? The transmission lines get heated up. Here we're heating up not just the water, but also the exhaust and all the parts of the turbine and all this kind of stuff. And all of this converting of one form of energy to another leads us to whatever energy the coal gets out, we only get some fraction of that energy or some percentage of that energy as actual energy down here down the line at the building. Now, we're not going to talk about this too much in this class, but it's just a general idea that nature requires an energy tax every time we convert from one form of energy to another. So generally speaking, the most efficient ways to do things are to have the fewest number of conversions from one form of energy to another. So in this first section, what we're going to talk about is spontaneity. And spontaneity is something that you're absolutely familiar with, but you may not have thought about it in these terms. Spontaneity essentially means processes which occur without outside intervention. Okay? If something is up in a tree, right, a branch, and it breaks, the branch falls down spontaneously. We do not need to put any energy in to get that branch to fall. It happens spontaneously. But if we put a birdhouse and we tie it to a tree and that falls down, if we want to get it back up, that will never happen spontaneously. The birdhouse will not spontaneously jump back into the tree and hang itself back up. We have to put in energy to make that happen, usually a human's energy. So spontaneous processes occur without outside intervention. And we're not going to have a book full of examples, but here are a couple of examples. Water evaporates at room temperature. Water naturally, spontaneously evaporates at room temperature without any outside intervention, assuming that it's in an open container. Heat flows from a hot object to a cold one spontaneously. We do not have to force the heat of a hot object to flow into a colder one. If you take a hot cup of coffee and you accidentally leave it on your counter in the morning, the heat flows out of this cup of coffee spontaneously into your counter and your kitchen or whatever the case may be. But the opposite never occurs. You never have a cold cup of coffee that spontaneously turns back into a hot cup of coffee. Now, if you put it in the microwave or you had, this kind of thing, you put it into a pot and you heat it up, you can heat it up, but you have to have energy, and this is not spontaneous. Non-spontaneous processes require energy input to occur, as the two examples we just gave. So here are a couple of examples. Baking a cake. A cake's not going to bake itself spontaneously. But if you add heat energy, you put the cake in the oven, then the cake bakes. Another non-spontaneous process we already talked about, moving an object up against the force of gravity. And I gave the example of the birdhouse. The birdhouse will fall down spontaneously. It will not go back up spontaneously. So now we want to look at some different processes and comment on their spontaneity of whether they will occur spontaneously or not. And the reason that we're going to look at this spontaneity idea is that eventually it's going to get us to entropy, which is a new idea. And it is also going to get us to the idea of Gibbs free energy. So here, I could ask the question, which direction is spontaneous? And everybody knows the answer. The house doesn't start looking like this and then spontaneously start to look like this. In fact, it's quite the opposite. Someone spent a lot of energy, or many someones spent a lot of energy to make the house look all nice and perfect. But spontaneously, over time, the house will degrade. One way of thinking about why this happens is there's an infinite number of degraded houses, and there's only one perfectly nice house. So for example, if this house gets a chip in the paint, okay, that's just one of an infinite number of things that's not perfect that could happen. However, that chip spontaneously forming back to this nice perfect paint is extremely unlikely because there's only one perfect paint state and an infinite number of non-perfect paint states. So which direction is spontaneous is surely that the nice house turns into the crappy house, if you will. Let's look at this more in terms of a chemistry example. And we talked about this a little bit in a previous chapter. Here we have a bunch of gas atoms in a flask. And here we have no gas atoms, or said another way, we have a vacuum. If we open this stopcock, we end up with a situation where the gas particles are evenly distributed. Now, if we look at which direction is spontaneous, do the gas particles go from evenly distributed to all on one side and a vacuum on the other, or do they go from all on one side and a vacuum on the other to evenly distributed? And of course, the answer is right here, but also common sense tells us that they're going in this direction. They will spontaneously go from organized to less organized, if you want to use those words, like the house, or they could go from more ordered to less ordered. But they will not spontaneously do the opposite. The reason for this is, again, statistics. There's only one ordered state where all the gas molecules are on this left side and none are on the right side. There are many, many, many ordered states, or many, many states where they are evenly distributed, because this gas molecule could go over here and this one could go over here and this one could go over here. And I mean, you could do the math, but there are lots and lots of combinations that look like this, where individual gas molecules are on different sides, and only one that looks like this. This is statistically much more likely, and therefore it spontaneously travels in this direction. It does not spontaneously travel into the statistically extremely unlikely situation. So you will never see a gas, spontaneously form a vacuum. That doesn't happen. Here's an interesting one that may make you nervous, okay? But listen to the whole thing before you get nervous. So if we look here, diamonds can spontaneously turn into graphite. Okay, as everyone knows, diamonds are valuable. Graphite is the stuff in a pencil, the lead of a pencil, so not very valuable at all. So diamonds are spontaneously turning into graphite because this is a more ordered state and this is a less ordered state, so the spontaneity works in this direction. But as we're going to mention when we sum this up in a minute, we need to be really careful when we think about spontaneous and we think about rate. All right, we talked about kinetics before, and just because something's spontaneous doesn't mean it's fast. Now, I do not know the exact time that this takes, but if it takes 10 million years, one doesn't need to be super worried that their diamond is going to turn into graphite anytime soon if it takes 10 million years for this to occur. So, even though a process is spontaneous, does not mean that it is going to be fast. So therefore, this is not a major concern, even though we are going from a more ordered state to a less ordered state, which is a spontaneous process. Here's another spontaneous process, and this is the transfer of heat. Here we have the hot object X represented by red and the cold object blue, Y, represented by blue. If we put these two objects together, then what happens? Well, spontaneously, the heat will flow out of X into Y. X becomes colder and Y becomes warmer, or we say another way, heat flows from hot to cold. And this is just something we were familiar with. This is a spontaneous process. Note that the opposite is not a spontaneous process. If we have two objects at the same temperature, heat never spontaneously flows to make one hot object and one cold object. For the same reason that the gas molecules do not flow from two containers back into one container, because it's very statistically unlikely, this is the same thing. They're not going to flow, and the heat is also not going to flow spontaneously to have lots of heat on one side and less heat on the other. It flows in the opposite direction instead, where hot heats up the cold, and you get an even temperature for X and Y if you wait long enough. So to review, spontaneity has nothing to do with rate, okay? So it could be super slow, like diamond turning into graphite. Yes, it happens spontaneously, but it doesn't happen quickly. The other thing here that that we need to point out by way of review is that spontaneous processes are not reversible. And we talked about this in several examples, right? Heat flows from X to Y. It doesn't flow from XY being at the same temperature to form X and Y. So it occurs in one direction, but not in the other. So generally speaking, there's a net release in energy when a process occurs, and condensed energy becomes less condensed. In a later section, I'm going to show you or give you access to a video where someone does a really nice job of explaining the concept of entropy in terms of condensed energy. Because entropy is a difficult concept to wrap your head around, I do recommend you watch this video when we get to it. So we already talked about this. The other thing we should point out here is if we have this hot and cold object, which again spontaneously flows from hot to cold, but it doesn't spontaneously flow from the two same temperature objects to form a hot object and a cold object, there's also going to be a practical energy tax here, because you're going to lose some of this heat energy to the surroundings. So if you look at these two objects will have more heat energy in total than these two objects, because some of this heat will not just flow into Y, it will likely flow into the surroundings, even if you have a very well insulated system. Now, if you theoretically have a perfectly insulated system, that will not happen, but that's more theoretical than practical. And then in a spontaneous So if a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. Said another way, spontaneous processes are not reversible. There are some reversible processes, and these reversible processes are at equilibrium. We have talked about equilibrium. In the case of equilibrium, there's no net change in energy for the equilibrium process, because the rate of the forward reaction and the rate of the reverse reaction are exactly equal. Therefore, the net change in energy is zero. Okay, so that can happen for reversible processes, but reversible processes are at equilibrium. So now I'd like to go over one example here where we decide whether these following processes are spontaneous or not spontaneous, and mostly these are just common sense, okay? So it says methane burning in the presence of oxygen. This one is actually challenging because people will always say, in order to get methane, which is the major component of natural gas, to burn in the presence of oxygen, you have to light it. You have to add a spark, or you have to, light it. So they say this is not spontaneous because you have to add heat energy. But that heat energy is what's providing the activation energy of the reaction. Once the reaction starts going, this is spontaneous. If you light methane, it will stay burning until you run out of methane, essentially. So this process is absolutely spontaneous. So if this process is spontaneous, what about carbon dioxide and water forming methane? So here we have methane, CH4, plus O2. And if you remember back to combustion reactions, this forms carbon dioxide plus H2O. This is a spontaneous process. And if we wanted to balance it, we would need to make 2 H2O and we would need 2 O2s in order to do that. This process is spontaneous. So if I take CO2 and water, will they reform methane and oxygen? No, it doesn't work that way, not spontaneously. Now, can plants do something similar? Can they take carbon dioxide and turn it into hydrocarbons? Absolutely, they can do that, but they're not doing that spontaneously. They have to add energy to do that. So this, the opposite process, is non-spontaneous. A bike going down a hill. We all know that a bike, if you sit on it, you don't even have to pedal. It will go down the hill spontaneously. But if we did the opposite, I keep wanting to add an E there. If we do the opposite process, a bike going up the hill, we all know you have to pedal the bike a lot to make it go up the hill. So bikes spontaneously go down the hill, but they don't spontaneously go up the hill, the reverse process. Sodium chloride, which is table salt, forming sodium metal. Well, I've never seen table salt turn into sodium metal. This is a non-spontaneous process. But if I mixed sodium and chlorine gas, they would spontaneously form sodium chloride. So the opposite process would be spontaneous. So I hope this gives you a little bit of an idea of the difference between spontaneous and non-spontaneous processes. In the next section, we're going to look a little bit more deeply into entropy.